Thank you very much for coming to the last session of the Symposium, Technical Symposium. I think this is theme number 8. It's my great pleasure to actually welcome my colleague, Professor Ken Elwood from the Department of Civil Engineering. He's the chair of this session, and together with Mr. John Shestopidov, from Senko engineering firm. Without any further delay, Ken, I'll give the podium to you. Thank you.
All right, thanks, Tony. Final session. It's been a really great symposium. Like everybody else, I'll thank Tony for all his efforts, but also the whole organizing committee, the students who have been helping out all along the way. We couldn't do it without you guys helping. So appreciate that. I promise in this presentation here, we've had a lot of very in-depth look at engineering and advanced technologies and detailed calculations. No equations here. Not that I don't believe in equations, but maybe we need a dose of something else. And I've changed my topic a little bit, and you'll see the title is somewhat modified. I'm going to, whereas other presentations have been offering answers, I'm going to be asking questions. This is not a presentation about a research project that's done. It's not even a presentation about a specific research project. It's just questions that I have in my mind that I want to share with you based on some experiences in Christchurch primarily. I had hoped to bring in as well some aspects of L'Aquila, and I will bring those in, but as you can see, L'Aquila is much smaller than Christchurch in the title. And they'll be represented that way. So let me start off talking about these two earthquakes. The cities themselves are actually quite different. I mean, Christchurch, population of 375,000 or so, very important city, largest city on the South Island in New Zealand, economically very important to the country. L'Aquila is much smaller, much older. That's reflected in the type of buildings. But still, they're both dominated by masonry and concrete buildings. But the earthquakes themselves in these two cities are very similar. Basically the same magnitude. The one occurred during the day, one occurred at night. But distance from the center of the city, the central business district, CBD, is about the same. The depth, both very shallow. And both have caused a lot of damage and a lot of ongoing issues in recovery. And so it's some of these issues in recovery that I want to focus on. Let me first introduce you to the Christchurch earthquake. Many of you are familiar with aspects of the Christchurch earthquake. You're familiar with the fact that the February 22nd event, which I will mostly focus on the impacts from that event, is actually one event within a series of events that started in September of 2010 off to the west of Christchurch City. The February event occurred here, just some 8 kilometers from central Christchurch, and aftershocks have continued. You're aware about the collapse of the CTV building. Dr. Adebar showed this. You're probably aware of the extensive damage to masonry buildings in the city, particularly to their heritage masonry buildings in the city. You may have even heard about the ground motion recordings in the city, and these are just the response spectra recorded within the central business district. The red line just showing the mean response there, and you may even have heard about comparisons with code, where notably it's very close to what they would expect as a 2,500-year event for Christchurch, and which notably is very close to what we would expect for a 2,500-year event for, say, Victoria. So the demands are something similar to, are relevant for us from a design perspective. But I want to actually talk about some aspects that are maybe beyond those things that you've heard about and some of those impacts that go beyond just the structural response. Some of you may have heard that shortly or immediately after the earthquake, there was a cordon put up around the center part of the city. And this cordon basically controlled access to the whole central business district for years. Immediately after the earthquake, it was about this size. That's hard to imagine what that size is, so it's good to put it on a map that's maybe a little familiar for our visitors from Shanghai. This is downtown Vancouver. So if we were to put that cordon on the downtown Vancouver, that's all of downtown Vancouver cordoned off. By May of that same year of the earthquake, that cordon had gone down considerably, but still, that's most of the core downtown area of Vancouver. The main economic center of Vancouver would be shut down if that were to mirror here in Vancouver. Even now, even this summer, there's still a portion of a cordon left in Christchurch. And it's shrinking all the time, but it is still there. And so one question is why? Why was that cordon needed? And it entirely was driven by, the initial setup of that cordon was entirely driven by safety. There was a large concentration of unreinforced masonry buildings in the downtown core. And perhaps the large devastation to those unreinforced masonry buildings and the precariousness of the remains of those buildings may have been one of the impetuses for putting up the cordon around the whole area right to start off with. But there's also the issue of the continued aftershocks, and the aftershocks occurring not away from the city, but right under the city. And so to ensure safety, by far, was the main reason why the cordon was initially established. But then it was discovered that this cordon facilitated many things. It facilitated immediate response. It kept people out of the area while urban search and rescue got in. It kept people out while building assessments were being done, so that engineers could go through buildings undisturbed and get those building assessments done quickly. It facilitated building demolitions, which has become a major topic in Christchurch, and I'll talk about in a few more slides. And it has even facilitated the planning of a new city. With the number of demolitions that are occurring in the city, there are opportunities now for the redevelopment of Christchurch. And with that cordon there, there's some ability to manage that development of that new city compared to if it was not there. And so in general, the cordon was accepted by most people. The management of access to buildings and to businesses inside the cordon in order to get your important materials out, there was concern. And that's something that needs to be thought of ahead of time as to how we're going to access those businesses inside of a cordon in the future. I mentioned the demolitions in the downtown area. This is an overhead shot that was taken several months ago now. And at first, if you don't know Christchurch, you might think, oh, well, it's just the downtown area, until you realize that all of those yellow squares used to be buildings. And then when you realize that the X's are buildings that have since come down, and there's probably, I know of a couple of others, as I was looking at the slide just a minute ago, that I've missed. Over 70% of the buildings in the downtown core will be demolished. Question is this acceptable? Is this acceptable performance for a community? Why have these demolitions happened? Well, they have to be registered under a certain category with the agency responsible for recovery in the Canterbury area. And 80% of these buildings are actually registered under safety, that they were concerned for the safety of the building or the remaining life of the building, and that is why they've been demolished. Another 20% have fall under this category of being determined to be uneconomical to repair. And it was cheaper to build a new building than to repair the existing building. I have to say that likely insurance has played a large role in the number of demolitions that have occurred. And certainly insurance comes into issue when you're talking about assessment of repair versus demolition. And even some of the 60% insurance likely played a role in the assessment that it fell under the safety category rather than uneconomical to repair. But the CBD is starting to come back, and some of that is happening by businesses wanting to get back into the city. There's concern that Christchurch is becoming a donut city with a hole in the middle and all development around the outside. And so some business advocates, central business district advocates have been pushing to try to open up some of the area for businesses to move in. And this is the old mall area in the downtown core that was very heavily damaged, unreinforced masonry buildings. It was all torn down, virtually all torn down in demolitions. One business leader had the bright idea to bring in shipping containers and put these shipping containers together in interesting ways and make a new mall in the same area. And this is not just important for the businesses to move back and to develop economic activity in the central business district again. It's also important for the social fabric to bring people back to the city and to create a place, even by putting it back in the same place where people were used to going before. The same mall area was important to the recovery. I've talked so far about the central business district. You also may be aware that there was huge damage to residential areas, particularly on the eastern side of the city. This is the central city here, due to liquefaction. And this is repeated liquefaction after all of these aftershocks. And this is just a map showing the extent of liquefaction, the red, of course, being the heaviest liquefaction, and then some degree of liquefaction in other areas. And this is only for February, but the same map reoccurs for other events. How did they deal with this? Well, they assessed the areas of highest liquefaction as requiring involvement of multiple homeowners in order to rehabilitate the land, in order to rebuild. And that was felt to be uneconomical and unfeasible within a short period of time. And so they took this area of very high liquefaction damage and lateral spreading damage around the river and the government said, we will buy your house from you and you get out. No houses in this area. Very difficult decision, difficult, big impact for the people, but it made a very conclusive decision so that people could move on and move to recovery faster. All the rest of the yellow areas here are felt to be, the bluish areas are felt to have some liquefaction risk and need further assessment. These are the people who are actually in the biggest uncertainty area. They don't know what to do. Whereas those who are in the red area, they've got a clear line where they go, their house is bought, they get the money from the government, and they move on. And so these choices that the government makes after an earthquake have an important impact on how people recover after the earthquake. This is just to indicate the dark blue here is showing that roughly only 30% of the insurance has actually been settled on housing in Christchurch. That's a big deal, particularly because New Zealand is very heavily insured. For housing, they're probably about 90% of the homes have insurance. And so that means that over about 70% of the homes have yet to have their house dealt with from the earthquakes. I mentioned that New Zealand is very heavily insured. In terms of the percentage of losses being covered by insurance, New Zealand is at 80%. This is far higher than most other countries around the world. And this starts to make you wonder as to what sort of impact does this high level of insurance have on the ability to recover? And is there a tipping point at which maybe insurance starts to hurt rather than help insurance? And perhaps in the case of New Zealand, the insurance is coming primarily from private, although private government partnerships. But perhaps when the government is involved as acting as an insurance company, as is in the case of L'Aquila, then perhaps they can keep in mind other aspects, the collective of the area, when considering impacts on recovery. Well, then I'll turn to L'Aquila very, very briefly. I'll keep this quick. So L'Aquila also had a CBD, a cordon around its central business district. The central business district was smaller, so it's a smaller cordon. But that part of that cordon still remains today, 4.5 years after the earthquake. I was there just in July and took these pictures. And unlike Christchurch, where the CBD is flattened, it's not flattened in L'Aquila, but instead they're all shored up empty buildings, which is, and this is partly a function of the decision by the government to focus the initial recovery outside of the central business district. It said, these buildings, these older masonry buildings in the middle of the city are difficult to deal with. We're going to deal with all of these more modern reinforced concrete buildings first, get them going, and then we'll move into the city. So it still sits. There are a couple of interesting observations from residential areas in L'Aquila I want to share with you. In contrast to Christchurch, where most residential is in single-family, one-story wood frame homes, residential in L'Aquila is mostly in multi-story reinforced concrete with infills buildings. And several of these suffered damage with loss of the infills. Mostly it was non-structural damage. Of course, there were the cases of some collapses within L'Aquila, but by and large the damage was damage to the non-structural partitions. But as you can see, there's many of these buildings still standing there today with those partitions on the ground. And a lot more of these reinforced concrete frame buildings are starting to move over towards demolition or make the decision to demolish. And you start to wonder, well, why are they choosing that for these buildings as opposed to the downtown area where the masonry buildings are being kept? Well, it's partly due to the high cost of the non-structural components with these clay tile infills. And as well, of course, there's much lower heritage value in these reinforced concrete. Another interesting issue is that because most of these are condominiums have multiple owners, it takes longer to make decisions. All of the owners need to participate in the decisions. And I see my Italian friend in the audience laughing, because Italians, of course, like to challenge each other when discussing, when making decisions, perhaps. But I don't think this is an issue isolated to Italy. I believe that maybe us here in Vancouver need to keep this in mind, considering our concentration of condominiums in the city. I throw this in for John. Many of the school buildings in L'Aquila are still closed. And a lot of these are closed not due to structural damage, but due to non-structural. And here is an infill that collapsed into a classroom. Perhaps good, it might be of value when talking to owners of buildings school buildings in BC. Let me hit on a few points related to resilience. I think I'm right at the end here of my time. But resilience is something where we need to consider the impact on the community as well as the time to recovery. And I want to emphasize here the fact that this is an impact on the community. It's not just simply one building we're talking about. It's a collection of structures. And so we need to start thinking about moving from one to many, from building to community, and from design to post-earthquake recovery. We're not good enough with just simply just design of a single structure. We need to think about the whole loop. We need to be transparent. These are just some examples of impacts from Christchurch where there have been drops in, say, population, drops in tourism, and in some cases, increases in construction permits, of course. And the question is whether all of these impacts, I won't list them off here, are tolerable, really. And what is the role of the engineer in all of this? And what is the role of engineering research? And I want to get this one in here because we've just had a session talking about performance-based design. And as we move in that direction, I believe it is the right direction. We need to realize that part of performance-based design is this loss analysis. And this loss analysis must be done with an understanding of all of the factors that play into those losses. And some of that is simply the decisions that come into play in that post-earthquake environment. We need to evaluate our codes and decide whether our design code objectives of life safety are good enough. We need to assess what is the cost of better performance. And this is just a very simple study done by a consulting firm in New Zealand where they looked at the costs of buildings in various different cities in New Zealand with different seismicity, and they found they were very, very similar. That the differences were not driven by the seismicity. They were driven by the desire to have wood paneling on the walls, nice carpets on the floors, and granite countertops in your kitchens. There has been a move in Christchurch to start rebuilding with innovative systems, with base isolation, even when it's a regular building, even when it's just a building for your standard businesses, your ma and pa, corner store shops. And so resilience is perhaps a way in which we can start bringing these new technologies into structures. But we have to be aware that 95% of our buildings are still going to be conventional. And so we need to figure out what sort of systems are more or less damage tolerant. And we need to maybe think about having some variety in our structural systems within a community so that when we have that earthquake that affects a particular structural system, it's not repeated over and over again throughout our community, that there's maybe some variation. Let's not put all our eggs in one basket. We need to also think about post-earthquake assessment. So much of what we're doing is thinking about new design or mitigation of existing structures, but we also need to think about that post-earthquake environment. How can we facilitate faster recovery in the post-earthquake? Perhaps the use of NDT tests to evaluate the capacity of structures after an earthquake. This is one of the big problems in Christchurch, and one of the reasons why there's uncertainty in the more decisions to go towards demolition, perhaps, is that they just don't know what the capacity of their structures are after being damaged. Of course, there's mitigation, which CSRN has focused on so much. And so I leave it now with just the idea that maybe we should change our focus a bit. Let's move perhaps away from solely a technical focus to more of a multidisciplinary, to take into account the aspects that influence the recovery. Let's move from simply focusing on the design of a structure to the post-earthquake response and recovery of that structure and the occupants. maybe moving from life safety alone to some form of damage tolerance. Move from talking about response of structures and engineering parameters to impacts on community. And again, this idea of changing from thinking about one to many, from building to community. With that, I thank you, and I apologize for going so long. So, that's not so bad. As chair of the session, I should not be taking a bunch of questions at the beginning, but I offer you this here as questions to think about. And as you know, we have a session tomorrow morning, a panel discussion, or a discussion session in the morning, and then a panel session. And I think that might be a good time for us to maybe start addressing and discussing some of these questions, if that's appropriate. So I'd like to introduce my co-chair for this session, John Shostopatov. John is the chair of the Standing Committee for Earthquake Design in Canada that sets the National Building Code, seismic provisions, and a well-known, knowledgeable local engineer involved with many different seismic projects. So, John.
Okay, thank you, Ken. Good afternoon, everyone, and thank you, Tony, for giving me a chance to speak here today. The topic that Tony wanted me to speak about was the seismic upgrade program of BC schools. Again, it's a performance-based approach, and just going to talk about some of the recent developments. However, I thought before, some of you may not be aware of the previous developments. So the SRG-1, it's the Seismic Retrofit Guidelines First Edition that was published in September 2011, and the engineering community has been using that to upgrade schools since then. SRG-2 is going to be issued in November this year with training sessions for the local engineering community, and those are the topics I'll talk about. For those of you that are not aware, it's over $2 billion is being committed by the BC government to upgrade the schools. And there's been in excess of $10 million spent on the development of the guidelines, testing and research at UBC and other locations, and a technical review board to review the designs to date. So this is a very significant program for just schools alone in BC, and I'll go through that. So what was done in the past? Again, from a performance based, and again, we have a specific hazard, 1 in 2475 here. There's demand spectra for the 3 different types of earthquakes that can occur here in BC. Different seismic records were calibrated to those spectra. Models were developed. Incremental dynamic analyses were done. And again, a conditional probability of exceedance. It all filtered in to get, for a variety of prototypes, what was the probability that that prototype would exceed a given drift that would achieve a life safety performance, and that probability of exceedance is set at 2% over the 50-year expected life of that school building. And I'll have just a few slides to sort of illustrate that. So, you know, and again, the records were scaled to the velocity spectrum in the range of about 1.5 seconds, which was estimated to be sort of the period of the buildings once they sustained some damage. And you can see the amount of motions for each record, 60 ground motions, 38 different communities, so a lot of different scaling and ground motions records to be applied for the 3 different types of earthquakes expected here in BC. Lateral deformation system, LDRS. This is the main lateral resisting system of the school buildings. 27 different prototypes that are consistent with the kind of buildings that exist today and the kind of new structures that we would be using to retrofit those buildings. And you can see the various type of structures that were looked at. And again, heights, etc. So a lot of modeling was done. This was all being done by UBC students and under Carlos. So again, simplified, I'll just get through this. These were all basically nonlinear shear spring models to try and simplify a typical prototype. Let's say this is a concrete shear wall. Okay? And again, backbone curves were developed for each of the prototypes. and the hysteretic loading, unloading, cyclic behavior within that backbone was developed specifically and uniquely for each of those 27 prototypes. And all that was run for different heights and all the different ground motions and all the different communities. In addition, Ken talked about out-of-plane walls collapsing. There's a tremendous amount of out-of-plane or partition walls, heavy unreinforced masonry and brick partition walls. 4 different prototypes were developed, and again, different heights, different thicknesses, whether they're loaded, whether they're just freestanding, and again, all those were run through the similar type of process I'll be describing. And lastly, diaphragms. The flexible diaphragms, either timber or metal deck, different varieties from very poor to very well detailed, were run through the system as well. So now we have the out-of-plane, the diaphragms, and the main lateral deformation system of the schools. For all of those, incremental dynamic analysis was run from 10% to 250% of the design level earthquake for that particular community. And you can see that's an old number. I think it's actually many of analyses were done and the data stored for all that, for those prototypes. And at the end of the day, in a probabilistic basis, and many people here worked on this, and in this room worked on this, and again, a probability of drift exceedance is actually now unique for each community and each prototype, and that was set at, again, 2% in 50 years, and a conditional probability of drift exceedance that if the design level earthquake, which is the 100% level earthquake, occurs, that was set at a 25% exceedance for each of the prototypes. So these were the 2 governing after all those analyses were done, and what at the end of the day, what the database will show is what is the required strength of each of those prototypes to achieve that 2% in 50-year drift exceedance or 25% conditional probability of exceedance for the design level earthquake. And again, this is when reporting to the school district and the public. If that probability of drift exceedance in 50 years was 2% and less, we said no retrofit was required for the school building. And again, you can see the different levels as, so that the public and the school districts could understand, is it very high? And right now, all the seismic upgrades are dealing with the H1 and H2 to get all of those down to this category. Once that $2 billion is spent, hopefully they'll put more money on the table to get the H3s and mediums down to the low-level risk. So this is where the money is being spent to get all these very bad buildings upgraded right now. All that data is basically a database, and what was turned, there's an online seismic performance analyzer. This is really an online tool that would allow a consulting engineer like me to do no dynamic analysis for a particular building, to use all the data that's been done to date, to all the engineers in BC now can consistently find out that for a 2% probability of drift exceedance, what capacity does that element need to meet that drift limit? And there's an assessment tool and an upgrade tool. In this case, the existing structure in this, it's hard for you to see, but it had 3% resistance, 3% of the weight of the building. The various other parameters were put in. Within a split second, the analysis produces this curve. It's red, it's a high risk. It doesn't have enough capacity. Okay? Then you go to the next stage, would be the retrofit, and it will tell you how much capacity do you need. In this case, it might be 23%. That's the capacity you need for this particular component to get to that 2%. This happens to be of a diaphragm, and it's that quick that an engineer can assess a building to see, is it high risk, medium, low risk? How much additional capacity is needed to get it to low risk? And you can play sensitivity with different prototypes, et cetera, different combinations. And what this does, it takes into account the capacity of all the existing components of the building, all the archaic, non-code compliant materials. And that's one of the beauties of it. Okay, so that's a quick summary of what was done to date. How am I doing for time, Ken? Halfway. Perfect. Okay, so SRG2, I'll just highlight some of the things that are being done. In BC, there's many 1950s and 60s buildings that are concrete moment frame but have infill masonry. Previously, there was no prototype to that. What the engineers would do would either saw cut these walls to eliminate them to allow the flexibility of the moment frame and make sure these didn't contribute to cause accidental torsion or make the building behave in an unknown manner, or remove them, or etc. So, but now there's been 3 new prototypes developed where all of this resistance which is there can be utilized. And again, they're just designated masonry 4, 5, and 6. Based on the ratio of the capacity of the concrete frame to the masonry itself. Based on that ratio, it puts it into a certain category, as well as the aspect ratio of the wall height to width ratio. And again, there's kilometers and kilometers of these walls that can now be utilized to further reduce the cost of seismic upgrade of the schools utilizing their capacity. So that's a very important addition. And again, like anything else, there's backbone curves that have been developed. There's loading and unloading within that. Various plateaus for the different types of walls. And again, that same analyzer will produce, for example, in Vancouver for a 3-meter wall on site class C, there's a certain amount of resistance that you'll need to get from those walls if you wanted those walls to take 100% of the capacity for the seismic resistance. If the walls had half that amount, well, then maybe you just have to add some additional components to bolster the remainder. So this is I see as a very important step to reduce the costs further here in BC. I believe Armin talked about this a little bit this morning. Seismic Performance Analyzer 2 is in the process of being developed, and this will now be right now the guidelines are up to 3-story buildings. This is intended now to go up to 8 stories and used for Ministry of Advanced Education here. Whereas before the analyzer was basically a database using it for prototypes, this analyzer can now be building specific, doing the same kind of incremental dynamic analysis, probabilistic combination for a specific building where you can put in the story heights, the moment capacities of the walls, the shear capacities of the walls, the soil structure foundation at the base, run all that same analysis and come out with that same probability of drift exceedance of 2% 50 years or some other similar parameter that's being worked on. And again, I think Armin talked about the reason why this is being able to be done within minutes, once this is developed. Another big item right now, and Ken talked about partition walls collapsing out of plane, which was good. Again, there's kilometers and kilometers of 100-millimeter thick, unreinforced concrete block in these schools. Maybe hard to see, but here's some lockers in a corridor with the block walls here, and here's a typical classroom partition wall with the whiteboards, etc. on these. All these are 100 millimeters thick, unreinforced, high probability of collapsing out of plane. The current cost to replace or restrain these is about $200 a square meter. For a typical school, this might be $1 to $2 million. Times 100 schools, it's a lot of money. If we can save 10% of this cost, we're going to be saving a significant amount of money. So we're looking at ways of effectively retrofitting these. One side is better than 2 sides if we can do it on one side only and not disrupt it. And again, UBC is going to start testing this this fall. And again, the walls are being built. This is just some samples of the different widths and heights that will be tested. And currently, there's a limited amount of options that are being tested. Ones where the walls are just grouted on the top and bottom to the concrete slabs. And where there's a gap right now, just steel angles will be put in here just to restrain it from flopping around there. This is sort of the basic. We're looking at cutting slots or just holes on one side of the masonry, inserting 9-gauge, very small diameter galvanized wire, grouting up those at a fairly large spacing, just hopefully enough to keep these walls to survive the design level earthquakes for out of plane failure. So those are going to be tested. Again, typically it's very easy to put a steel section just above the height of the typical door. So we can run these from concrete column to concrete column or whatever. And again, reduce the unsupported height of these, come up with trying to get some cost-effective details one-sided, and again, so we don't disrupt too much there. And again, typically in the past, metal studs on one side have been used. We're trying to use even cheaper unistruts, off-the-shelf unistrut sections that can be bolted to the masonry on one side to see how these perform, and are they more cost-effective than conventional stud walls. So these are all being tested. They'll be tested on the UBC shake table, and hopefully we'll get some results shortly. Briefly just touch on the last couple items. New to this one is liquefaction guidelines. Professor Finn in the audience here is leading the charge on the geotechnical aspects of producing these guidelines for the engineering community. I'm looking at the structural aspects because there's many schools that are sitting on a non-liquefiable crust over a liquefiable soil with all kinds of permutations of foundations. And again, the very simplistic thing that we're doing is to, again, if there's differential lateral movement where there may be some bias in the slope, and that there may be rupturing in the crust and movement of this footing relative to this one, causing some distress on the system. And again, delta H over H is a parameter we'll be using. Similarly, there's always differential vertical movement as the amount of settlement and liquefaction in one area may be different than the adjacent part of the school. And again, a parameter of delta V over L. And at the end of the day, we're coming up with a combination of, there's a residual drift after the transient shaking. We believe we're allowing for the residual drift to be 20% of that peak limit that we've allowed for it on the various components. And again, we'll have the differential vertical, differential horizontal, and we'll give the consultants a drift limit that they have to live with in combination that the structure has to be able to accommodate. If not, some kind of remediation has to be done. A system that we've used very cost effectively to limit the horizontal is we've put ring beams around buildings, grade beams outside of the building, basically to set the differential horizontal to 0, and one of those components in the equation disappears, and this has become a very cost-effective way to deal with that item. Lastly, 3 slides, Ken, and I'll sit down. You talked about post-earthquake evaluation. The Ministry of Education will pay for instrumenting every retrofitted school building in BC to get some post-earthquake data on ground motions and motions of the structure. The school district just has to pay for the annual maintenance to keep the instruments working. Whoops. Sorry, let me go back. A key item of that is P-wave instrumentation, early warning. This will provide 5 to 30 seconds of early warning, depending on where the earthquake is, for alarms to sound in the classrooms to allow the students and staff to get under their desks sooner, as well as strong motion instrumentation, various parts of the buildings to provide data. Every school done so will have drawings prepared as for all the various components, what level of recording of that instrument is deemed to be a threshold at which it's acceptable or unacceptable, and this will be available at each school for any engineer to use for post-earthquake evaluation, as well as information on damage states, the backbone curve that was used to do this. So all this there will be to enhance that typical ATC visual inspection so that these schools can be reoccupied faster after small, medium, or even large earthquakes. And I think I'll leave it at that for now.
I think we have time for a question, if there's some.
John, I just wonder, that they spent $10 million developing this and committed $2 billion to do the repair. Can you give us some idea of how much they've actually spent on school repair to date, and your sense of will they really be spending $2 billion, or is that just a problem?
Oh yeah, no, they definitely will be. And
how much have you done to date?
They've probably spent close to $800 or $900 million to date.
Okay.
The next 3 years is $150 million has already been. I mean, that's the projects are all lined up, and No, it's,
Thanks,
they're trying to fast track.
John?
Yes?
What twisted the government's hand towards this magnificent work?
Sorry?
What did twist the government's hands in spending $2 billion?
Oh, what twisted the government to spend this? I mean, again, they started this. This started in spits and starts after the Lower Crater earthquake. So basically, in 1990, they started doing upgrades of some schools. They found it was too expensive, and it stopped. And some other champion came along. They did a few schools, and it stopped. And eventually, a parent group, that had significant lobbying access to lobbyists at the government level raised this awareness to a level that the government really had to do something. And then once a champion sort of emerged within government itself, the groundswell moved on.
Thank you.
Oh, no, sure. Okay.
Our next speaker is a PhD student here at, how do we start this? PhD student here at UBC, working with myself and Dr. Adebar, Jeff Yatha, and he's going to speak on the sort of risk we have in our concrete buildings in Vancouver and sort of characteristics we're discovering in these buildings.
Great. Thanks a lot, Dr. Elwood. So, like Dr. Elwood said, I'm giving you a brief talk today on sort of my research program, and I've titled the talk Seismic Characteristics of Pre-1980 High-Rise Concrete Buildings in Vancouver, but really I'm going to be talking about sort of how we've gotten there, and then at the end I'm going to start giving you some statistics. Okay? So a little bit of an introduction to this project. The motivation of it is really coming from a global interest in what non-ductile buildings, how many non-ductile concrete buildings, not just concrete, but in buildings in general we have, and specifically concrete buildings. Okay, so after, pick your number from the past 10 or 20 years, people have been really concerned about this because these buildings have been shown to have a pretty high risk of severe damage or collapse in a number of earthquakes throughout the world. So when people started looking at this idea, of course, there's the question of analyzing the buildings themselves and determining the vulnerabilities. But there's also the issue of simply how many of these buildings do we have? What are their characteristics? What are their problems? Okay, so the first major step that most people have taken is to build inventories of these buildings. And a good example of this is the Concrete Coalition, which is attempting, their mission is to build a database of all of the concrete buildings in California, all of the non-ductile concrete buildings in California, I should say. But they're doing things on a very broad level, okay? And so then that raises the question for us, how about our buildings? How about the Vancouver buildings? So engineers, and I should include researchers among that, and building officials with, each progressive earthquake where we see damage of, our Chile, our Christchurch, people become more concerned and more interested about this. All right, so I started to look at this problem and come to grips with it. But before we start getting into anything else, I just want to give you a little bit of a history lesson here of downtown Vancouver. So this is a shot from Vancouver in circa about 1930, okay? And it's not too clear, but for our visitors, this is downtown Vancouver here, and I've just shown it on the map. You might be familiar with it by now, and sort of the angle we're looking at. And you can see that in 1930, there was a small cluster of tall buildings here. Remember, I'm talking about tall buildings. There's a small cluster of tall buildings here. But pretty much the rest of downtown is all low-rise residential buildings, okay? Let's skip forward to about 1970 or so. So pretty big difference. You notice sorry about the perspective changing a little bit. I tried to find ones with the exact same perspective, but I couldn't. Turns out there weren't that many aerial photos in the 30s. So now you can see this is downtown a little bit closer. We're looking from a slightly different perspective here. And you can see that there's still these same buildings that there were before. Maybe there's a few more of them. But there's an explosion of buildings in what we call the west end of downtown now. All right? And most of these buildings are residential buildings, as we'll see later on. My building stopped before 1980, but let's fast forward again. And here's a shot in 2007 from a different perspective. But you know what? Even better, just look at that really nice picture on the front of your book. Okay, that's an even one. That's from very very modern picture, and you can see all of downtown now has high-rise buildings. Okay, so there's really the trend has been towards that direction, and it continues today. Although we kind of run out of space in downtown, so now we're moving other locations. All right, so what are our objectives then? If we ask the question, how bad are our buildings? What do we need to do? You know, what are the goals of our project? As we've seen, there's many high-rise concrete buildings. All right, and as I'll prove to you later, most of them use concrete walls as the primary lateral resisting system. Okay, there's very few high-rise buildings compared to John's talk just a second ago. Very few high-rise buildings that use moment frames or other systems, okay? And this is just concrete, by the way. There are steel ones as well, although not very many. So therefore, we decided to narrow down the scope of the project, all right? Just because we don't want to have to deal with a whole building inventory, we want to get specific on these buildings. There's other people that have been doing building inventories in Vancouver. We want to get narrowed down specifically on these buildings that we've seen that can be such a problem, that possibly pose a higher risk because they're higher occupancy. So we're looking at 7 stories and taller, designed before 1980 as an estimate for when modern seismic codes came in. And like I said, we are trying to find detailed information on it. Them, I should say. So what do we have so far? What information do we have where we can, that we can use? With the City of Vancouver, we've collected information on a bunch of buildings. We have structural drawings of about 350 buildings, which we estimate represents about 70% of the total, right? Those other ones will be ones that drawings weren't available, or we suspect the building's concrete, but we couldn't get any specific information, etc. And the location of those buildings, as you can see, is clustered in downtown as expected. There are a few outside of downtown, but you can really think of it as primarily in downtown. Okay, so in order to collect our information, the next step was to make a database, somehow organize all this information, right? So I'm just going to lead you briefly through this database and tell you about why we made it the way it is. The database is structured so there's a basic building entry form where we're entering most of the basic information about the building, and then there's 2 subforms where we enter column information and wall information. So the building entry form, just collecting basic information, some information about deficiencies of the building, okay, just a general overview of what we've got. And then here's just a screenshot here, so you can see sort of the amount of information we're collecting. I don't expect you to look at it in specific, okay, but just the amount of information we're collecting on that form. The next form we're looking at is, or next form is just a technical word, but the next group of information we're looking at for each building is the column information. And this is the goal of capturing this information is just to try to get a feeling for how vulnerable our gravity system is. So what we're doing here is just capturing one column, which we pick as what we think is the most critical column. So, you know, smallest, highest gravity load, farthest away from most of the lateral system. We capture information about it like its ties and tributary area. And then we can use that information to try to estimate how vulnerable the gravity system is. So, little screenshot again, just a little bit of information. Okay, and then the last piece of information we're collecting is, remember, as I said before, most of the buildings use concrete walls as their primary system. So we're capturing information on the walls, including dimensions, reinforcement, and also possible discontinuities in the wall. All right, so, and then this form looks like this and actually carries on further. But so for each wall, we're collecting all the information on the wall. And then the idea is we can use that information later to assemble stiffness and strength properties about the building, you know, in a rough way. Okay, so next thing I'm going to start showing you here are some basic statistics from the database. Okay. So just some simple stuff. We haven't completed all of everything we're going to do with the database. It's quite extensive, but I just want to show you some basic results. So first, just want to prove to you percentage of buildings with walls as the primary lateral system, 98%. Okay, so Not a shock, but that's a lot. So I think we're doing a good job to focus on them. And then percentage of residential buildings out of the buildings we looked at so far, which are probably about 2/3 of them, 85%. All right, only about 11% are office buildings. So like Dr. Elwood was saying earlier, maybe that brings up questions about ownership. And note that this doesn't split into rental versus condominium units. Okay, we could actually, if we had the information, we could incorporate it later, but you can't get that from the structural drawings most of the time. Okay, so, and also I was just thinking when I listened to Dr. Elwood's talk, it is interesting that how focused Vancouver is on this type of building. So maybe that's not the most resilient thing in the world. And we have, there's this building, and then there's your single-family wood houses, and maybe not too much in between. All right, so this is basically just a plot showing the buildings we have. So on the one axis, just number of stories, and the other axis, I've grouped them into years, roughly based on code, changes in the code, okay? But also observations I made as well, and something I didn't think of, which was raised yesterday, is that probably a lot of these buildings were based on wind design. Okay, so I know you have to go back and look at the wind codes too, but you can see we don't have much right now in the database pre about 1950s. Okay, in the 50s we see some shorter, relatively speaking, buildings being built up to 10 stories, and then an explosion. Okay, in the early 1960s, a ton of buildings being built. Same thing throughout the end of the 60s, and then a slowdown in the 70s, but a wider range of buildings being built. Okay, a lot of different heights. Same thing in the late 70s. Next few slides I'm going to show. Next 3 slides. What I've done is taken a system characteristic such as, well, let me just flip to it. It's a little busy. Just don't worry about it. I'll explain in a second, okay? So what I've taken on the side is a system characteristic, in this case torsional eccentricity, okay, and compared it with a component deficiency, such as, in this case, column axial load ratio. So the idea is, right, the higher the torsional eccentricity in the building, the more demand will be put on the column, and then the more the axial load in the column will matter, all right? So the colors just correspond to the same colors we saw before, okay, but you don't really need to worry about that too much for this graph. And then the circle triangles are where there happens to be bottom slab steel through the column. Okay, they haven't put in integrity steel, there just happens some to be there. And circles are there's no steel through the columns. Okay, so I guess the first thing that pops out is thank goodness there's nothing up in here, right? This is the worst part, high eccentricity, high axial load ratio. Okay, there's nothing in here, which is great. It's sort of, it clusters down in this more reasonable area, and you can see sort of a curve here where it doesn't go beyond. And then we can look at things, then this is the kind of thing we can start looking at from our database, is this type of information. For example, these buildings up here, they have high eccentricity, but they have low axial load ratio, and they have steel through the columns. That's just coincidence, by the way, that those 5 or 6 up there have steel through the columns. It appears to be mostly random. These ones, on the other hand, well, maybe the torsional eccentricity isn't so high, except for this guy up here. But the ones remember, the ones in the circles don't have steel through the columns. So we've got a high axial load, some eccentricity, and no bottom steel going through the column at all. Okay, so possible vulnerabilities. Next one I want to show you, just taken another system characteristic, in this case our estimated lateral period, which we've calculated from our wall information. And then I've calculated the average wall thickness, okay, as just a rough measure of how vulnerable the walls might be, right? As we progress further into calculations from the database, we could theoretically, with their information, we could calculate actual compression block depths and compare it to the wall thicknesses, et cetera, but we're not quite there yet. Okay. Again, the critical area in this case is this zone. So we've got where we've got higher periods, right? So larger drift demands, and low average wall thicknesses. Notice that this comes from 6, right? So all of these buildings in here have an average wall thickness between 6 and 8 inches. That's, pretty low by today's standard, but clearly pretty common in that day. The other thing to notice from this graph is it's kind of hard to see, but the red ones are the early 60s. Okay, the green ones are the late 60s, and then the purple ones are the early 70s. Not a lot of data in the early 70s, but I think there's a generally increasing wall thickness over time trend, which is what we'd expect. It's both useful for us to know and a nice sort of verification of the database. Okay, last one I want to show you is, again, dots everywhere. Sorry about that, but this one is a system characteristic. It's discontinuous walls. So these are discontinuous walls that come down, and I encourage you to, well, maybe I shouldn't encourage you to look for these when you go downtown, but if you do happen to look for them, if you do happen to be walking along certain streets, which I won't name, but there are a lot of these buildings around where the exterior walls especially will come down and sit on 2 columns, and there'll be a big hole in the ground floor because it looks nice, I guess. So on the left here, we have percentage of discontinuous walls of the total. So, up to 60% of the total walls are discontinuous. And then on the other one, I put the column transverse reinforcement ratio. So the column that these walls are sitting on, their transverse reinforcement ratio. Okay, so again, here's the problem zone. A lot of discontinuous walls, not very much transverse reinforcement. We could do a lot more of those plots, but just wanted to give you a flavor of what we're coming up with right now. Again, we can use those things in a lot of different ways to either build, just identify the characteristics, or to use them to figure out which buildings are the worst. There's a pretty broad scope in this project. So future research in this direction is using the database to generate even more statistics. So like I said, strength and stiffness calculations are being refined. So hopefully, it'll never be perfect, right? This is just a simple model, but we could hopefully be able to calculate torsional periods and stiffnesses and compression depths and other important information like that. Continue to generate more plots. And a big thing that didn't make it into this presentation, but that we're working on is considering what happens when a building has multiple deficiencies, all right? Because if we're just talking about one deficiency, often that doesn't collapse a building. It's a combination of multiple deficiencies that collapses a building or causes extreme damage. So we're going to figure out a way to combine all those deficiencies. If this building's the worst on this plot and it's the worst on this plot, then that's probably a really bad building. More stuff we're going to be doing. Now this is sort of possible future research directions, is one thing we can do is use the database for specific problems. So if somebody comes to us or we decide to do ourselves, for example, they want to look into thin walls. What are the actual wall thicknesses in buildings in Vancouver? What are the wall configurations? We can tell them. We can give them the information for a realistic range of variables. Lastly, developing archetype buildings. Okay, so we don't. These are specific buildings. We don't really want to do we can do detailed calculation on a specific building, right? That's what an engineer would do. But we're looking across a broad range of buildings. We want to get the big picture. So we don't want to develop models that are based on a whole range of buildings. If we put all of those typical characteristics into one building, then we can do analysis on that building. Then we can find about, we can do hazard models or a global assessment of the system, et cetera, et cetera. All right, so that ends my presentation. Thank you very much.
Thanks for staying on time, Jeff. Any questions?
Yes?
You mentioned at the end there, so you plan to do some sort of nonlinear analysis of some of the typical buildings to see how they really behave.
Yeah.
Is that in the near term or further?
Well, that'll play in that. Well, in the medium term. Yeah, I'm just going to hedge at my bets and say medium term. But yeah, it's not the problem. The opportunity is that there's so many different things we could do with this information that we're sort of trying to decide. But I think we're leaning towards developing the prototype buildings and doing the nonlinear analysis of them, and the multiple what happens when the multiple hazards come together, what kind of typical hazard curves do we get off these buildings, etc.
Any other questions? All right. I think we're on to our last speaker of the day of the symposium. No pressure. Only standing between us and drinks.
Yeah.
So Majid is a PhD student, as he says, hopefully by the end of this week. Literally by the end of this week. And has been at UBC for just a couple of years now. And so he's going to talk to us about a collapse assessment of non-ductile buildings. But where the last speaker focused on walls, Najib maybe will focus on frames. So take it away.
Thank you, Dr. Elwood. So I've been a couple of years, but I really enjoyed it. It's hard for me to leave this place. So the title of the presentation is the collapse assessment of non-ductile concrete buildings. Because I knew I was the last presenter, I didn't put my whole thesis presentation here. It's only 2 chapters, so I'll keep it short. So a little bit background and motivation. As you can see in this figure, if I can get this right, yep. So this is like a screenshot of a part of LA County. Each of those black dots represent a non-ductile frame. And there's no need for me to emphasize during these presentations today. We all know there's a lot of these, and the problem with them is that this is what happens to them, unfortunately. And during these collapses, a lot of people lose their lives, a lot of money. But the main thing is that we don't always see these cases. There are some cases which buildings stand. I know this is not a building that you want to live in after an earthquake, but it's still standing, so we can't call this a collapse case. Most likely people were able to come out of it very hard, but were able to come out of that. So there is a need for research and probably in the industry to be able to distinguish between this case and this case. And we need that, as Dr. Elwood said, in order to move from a building to a community, we have to be able to distinguish between these 2 cases in order to study this region, to come up with regional loss or collapse performances. So there is a need for a new procedure to identify these collapse hazardous buildings. And it's something that's been done a lot of research on. What do we do in order to find these out? We use these standards. The current standards, which roots from about 20 years ago, they've ended up into AC 41 and 31. And I think the next one has combined these together. But what could be after that? What are the next generation of these standard codes, especially to come up with collapse? Where does the research and industry stand? One is HUMA P695, which they use this approach. It's mostly for newer buildings, but they use it for older buildings as well. There's some technical issues that we believe there are in there. One is for these type of frames, they use non-sibilant collapse, which is a little bit conservative. They only consider side sway collapse. We've seen in a lot of test data and after earthquakes that this is not the main source of collapse. The mode is probably gravity load collapse. How to deal with uncertainty and what they do with the spectral shape factors. So these are some limitations on that. There's another approach which is more research-based, is like the progressive collapse. Every component that reaches its collapse state or final state, we remove that. And this is highly computational demanding. And it's very hard. People who have done these analyses know that this is very hard to get to this stage. So we need something better than that. And we need something that could be useful for engineers and to be useful for those standards. So as I said, how do we be able to use some numbers, some indicators to find these collapsed buildings, the past earthquakes? We call those collapse indicators. There are design and response parameters. I'm going to explain in the next slide what they are, what we think have a correlation with elevated probability of collapse. So an engineer can open his booklet and look at the building and look at those parameters and see where it stands. If it has a high number, it has a higher probability of collapse. If not, it's a good building. So that's that booklet. That's what we're trying to build. So this is some schematics of potential collapse indicators. They fall into two different categories, design and response parameters. Design, we have two. We have a rapid assessment. It's like an engineer, when he goes to a building or just looks at engineering drawings and come up with these numbers. It's the transverse reinforcement of these vulnerable columns. And it can come up to component and system level. For the system level, it could be the ratio of the sum of the columns to the floor area, the area of the floor. The next category could be engineering calculations, which the engineer doesn't have to do any analysis. He just does some hand calculations based on the engineering drawings. It could be what's the ratio of the shear capacity to the flexure capacity. It could be the amount of gravity load those vulnerable columns, the shear column, the columns that are will have most likely shear failure. What's that ratio? These type of parameters, they fall into AC31 type of parameters. There's another category that we call AC41. These are response parameters, what we give out of response. It could be based on drift, similar to the school project. What's that limit for drift that you know your building is safe or not? Other parameters could be the number or fraction of columns in one story that experience shear or axial failure. That could be another parameter. So our objective was to come up with the methodology to choose and go all to the end to find those limits, similar to that school project. So this is the different steps that we came up with. Step one is to come up with the potential list of collapse indicators, whatever you can think of. The next step is to come up with a detailed numerical model. I'm going to explain why it should be detailed. Step 3 is do the seismic hazard analysis. Step 4 is how to consider the uncertainties and do the probabilistic analysis. Step 5 is our nonlinear analysis. The last step is our assessment and a post-processing procedure. So as I said, these are non-ductile buildings. And the nonlinear model that we need for these are very detailed. The focus of this study was more on non-ductile frames. So a non-ductile frame is a very important component of our non-ductile columns. And because we're trying to cover a wide range spectrum of these different type of buildings, we had to come up with a general model for these columns. A general, we called it mechanical model, which you can predict shear failure based on a mechanical model. It's the axial shear flexure interaction model. After shear failure, the shear friction, and the axial model as well. So the whole model for the columns, it's a mechanical model. It can cover a wide range of columns. Another important thing is to come up with collapse. How do we define collapse in our analysis? What we try to do is we try to come up with a system level definition. And for both beam column frames and slab column frames, we came up with two definitions for that. We implemented both in OpenSeas. So the main procedure is we look at a story level and we calculate the amount of capacity and demand. And as we all know, when demand goes beyond capacity, when capacity drops, that's what we call a gravity load collapse state. So for instance, if we have a slab column frame, our weak elements are slab column connections, and during an earthquake, when the drift increases, we have a decrease in our capacity. There's a point where we have our first failure. We have like a punching failure in our slab column connection. So we have a drop in our capacity. But we still will not have a gravity load collapse until we get the second one. And that's when our capacity at this point goes less than our demand. And that's what we call a gravity load collapse. This was very important and requiring our analysis. Otherwise, we would not have an objective definition of our collapse states. So it was very important, the seismic hazard analysis. We tried to mimic what's nowadays they call like CMS, the difference between UHS, which ground motions to choose. So we used that CMS, which a lot of people believe has a better representative probability of collapse. We consider uncertainty, both the ground motion and our model uncertainty in our analysis. For the nonlinear response analysis, there are two approaches, the IDA. We use the MSA, which you choose ground motions at each hazard level. And based on that, so these are at each hazard level, and in contrast to the IDAs, which you just use a specific set of ground motions, you just amp it up. And the last step was probably the most important step, was how do we post-process these results? How do we extract numbers from all these analyses? So it's slightly different for the design and response parameters. For the design parameters, as I said, we have one building. You can consider the left one. And it has, for one specific parameter, for instance, the transverse reinforcement, the average in one floor. What we do in our analysis, we start changing that only parameter, and we redo all our analysis. So we go from step 1 to 5 to come up with these collapse fragilities. What we can do is we can look at a specific intensity level, like MCE, and we can draw, based, again, the probability of collapse for that specific collapse indicator, which is the transverse reinforcement. And we can see as we decrease our transverse reinforcement, we're going to have a point which kinks up for the probability of collapse. What we have to do is we have to redo this for a couple of buildings, and based on that, we can find a point which is our limit. And we can use this limit and that booklet. There are different approaches. This was a relative approach. We just look at kinks. We can use approach which you choose a number, like polyclus of 10%, which is usually used in these codes. So you look at a specific limit for two different buildings. You see at this limit at 10%, what's the range of those collapse indicators? For instance, what's the range in that row? These are intensity-based. You can use a risk-based, which, again, we have the same building, the original building. We change the perimeter. We can combine these curves with the hazard curve, and we can come up with mean annual rate of collapse. So this is the mean annual collapse for a collapse indicator. And again, if we choose a specific limit, for instance, 1% or 2% in 50 years, for newer buildings it's 1%. So for these older ones, we can slightly relax it to 2%. We can use that to find our range, or we can go and choose a good building, a building that we know has a good performance, and use that as our limit. So there are different approaches that we can find these limits. We had to try this out, this methodology. So we choose three different types of buildings, three different buildings. They're all moment frames, but different heights from 4, 7, and 12, different bays. They fall into different framing systems, space or perimeter, and they're located in different locations. They're in the high hazard region in LA, or the 12-story building was designed for Vancouver. And the reason that we had to limit our analysis, I'm going to show later on, for each collapse indicator, for these three buildings, we had to do 10,000 nonlinear analysis. I used something similar that Armin presented at supercomputers to do that. But we had to limit that. So, that's why we limited to 3 buildings. Just to look at those 3 buildings, as I said, 2 different hazard regions. It's in LA or Vancouver. And as we can see, these are the collapse fragilities, the original buildings for those three buildings. The 4 and 7, and the purple shows for the 12-story in Vancouver. As we can see, it has a better performance, the original buildings in Vancouver. So just to show you some numbers. So if we go through those 6 steps of procedures, and for instance, for the mean annual rate of collapse for those transverse reinforcement, we can see how for the change in the collapse indicator, what's the change in the mean annual frequency of collapse. And as we can see, for the only building, if we choose this limit like 2% in 50 years, the only building that we can find a limit for is the 12-story building. It's that point. For instance, so the results show that if we choose our transverse reinforcement more than 0.005 in this building, we'll have a building safe enough to have probability of collapse less than 2% in 50 years. Our results show that for the 4 and 7-story building, unfortunately, we cannot reach this limit. We have to go to very high values. As I said, just to come up with this one curve, I had to do 10,000 nonlinear analysis. And this shows why there's a lot of analysis to be done, but how useful they could be. Another parameter that we can consider for design parameters are the maximum plastic shear capacity, the shear strength of the flexure capacity for these for this parameter for the collapse indicator, VP over VN, and again for that mean annual frequency of collapse. For that 2%, we can see only for the 12-story building we're able to go through that. And the results show that for about the range of 0.7 to 1, which usually we call the transition zone from the flexural to the shear columns, we can see only the 12-story building we can find a limit for that 12-story building only. And again, what we see for the 4- and 7-story building, we don't find a limit. We did this for 8 other collapse indicators. The same, we had the same results. And it shows for design parameters by itself, we cannot find one parameter that will be able to set a limit for it. And we have to do a vector of these collapse indicators. But the results are slightly different when we use response parameters. So what we did again, we used the results from our nonlinear analysis. So this shows the response for interstory drift. The points that we don't have any collapses, we have on the bottom. The points that we had collapses on the top. I used the maximum likelihood function to come up with these collapse fragilities. So it shows the probability of collapse for that response parameter. This is for a specific intensity level. I did that for a couple of intensity levels from 224 up to 2475. Again, if you use the seismic hazard curve, you can come up with the mean annual frequency of collapse for that collapse indicator. So what this curve shows is that if you choose for a specific limit, again, for 2% in 50 years, it shows that your drifts should be less than about 5% in order to have that rate of collapse. Again, we can use the risk approach, or we can use a specific intensity, for instance, the 2475. So if I use the 2475 for 2 sample buildings and a 10% probability of collapse, I can find those limits. So we did that for 4 different collapse indicators. I'm going to show only 2 of them. So for the percentage of columns in one story which experience shear failure, as we can see here, we have 2 district regions for the 2 type of buildings. For the moderate seismic region, 12-story building, it shows that if we have less than 60% of columns in one story experiencing shear failure, we'll still have a safe building, a building that has a probability class of less than 2%. For the higher region, it has to go down to 3%. The same results almost govern for when we use the intensity approach. But the interesting result here is that now we have some limits for the 2 types of buildings, and it shows the results are independent of the type of buildings for the 4 and 7 and the 12. It's only based on the seismic region. So these results are more promising. For the interstory drift, we can see the same thing. The results show that all different type of buildings in different seismic region the results are independent from that. If we choose about 3%, 3.5% as our limit, we can find that could be our limit. If our drifts are less than 3.5%, our buildings are going to be safe enough. And these results could be implemented in the future, the next generation of these retrofitting standards like AC41. We see the same results when we use intensity levels. So in contrast to the design parameters, which we had a big variety of numbers, and under response parameters, the results are much more promising. Just to conclude on that, so we came up with the methodology, how to come up with these collapse indicators, how to go from step 1 to step 6 to identify them, and to come up with some limits. We found the limits on each of those collapse indicators, and as I want to emphasize again, the design parameters were not that much promising, but the response parameters are very promising and can be used in future standards. So as I said, I want to keep it short, so I thank you all for listening to this presentation. And any questions?
Any questions for Majid? It's been a long day, and I think people are looking forward to the banquet. So Thank you very much. I maybe open the floor for any other questions for the speakers of the session. All right. Well, then I'd like to thank the speakers from this last session, and I'll turn it over to Dr. Yang to give us our marching orders.
All right. Thank you so much, Ken. First of all, I would like to thank all the presenters flying all the way to here, and our colleagues from UBC and students here for giving us such a whole series of wonderful presentations to make this a very successful symposium. So please join me to thank all the presenters. Thank you. Okay.